Good evening, everyone. We have space up here, so there you go. Sorry, that's a bad one. Okay, so I'm Paul Wahlbeck, Dean of the Columbian College of Arts and Sciences, and I'm happy to welcome you here tonight to Reaching for the Stars, Big Equipment for Big Science. So I'm pleased that we have a panel of experts. So let me introduce them in order here. So we have Leah Brooks, Professor of Economics and Public Policy and Public Administration. Professor Brooks studies federal spending on common goods, such as infrastructure and research, a topic relevant for tonight, along with the long-term economic effects that results from federal funding. So thank you for being here. Next up on the dais is Associate Professor of Physics and Department Chair in Physics, Alexander Vanderhorst. He is an astrophysicist whose research on a variety of high-energy cosmic transient sources utilizes state-of-the-art technology that we'll hear more about tonight. And then on the far side of the table is Nicholas White, Research Professor of Physics. He's an astrophysicist with a storied career, serving over 25 years at NASA and earning a Presidential Meritorious Rank Award in 2004 for his leadership before joining GW in 2019. So these series, the Dean's Conversation series, is an opportunity to hear from faculty about their expertise, especially as it relates to the issues of interest to our community. So this is one way that we can advance our twin mission as an academic institution. That is, first, advancing knowledge through discovery, and second, through the teaching of the next generation of leaders. So I'm thrilled to have this conversation about science. That's the theme of our Dean's Conversation series this year, science. The last session we did basically biomedical science and trust in science. Today we're shifting from people to space and discussing astrophysics and the funding of science. And then we will have another session in January on January 21st. So look forward to seeing you then too. But this is an opportunity to hear from our faculty and to hear their expertise on issues of importance. And certainly the discussion of science is a critical topic in our day today, whether that be from the role of science and scientific expertise in policymaking, or the role of grants and federal funding and what's going on in that area at this point, but the role of science in our society and in our world and beyond our world is our subject today. So I'm thrilled to welcome all of you to this conversation. So we're going to start off by doing a little bit of discussion about the discoveries that Professor Vanderhorst and White have made in astrophysics. So beyond the beauty of some of the images that we see in the media, and these are clearly clickbait for most people in society when they see the pictures from the Hubble Space Telescope and all the other things, what do we learn from those observations? Can you give us a brief elevator pitch, so to speak, about your astrophysics research?
Sure. So thank you very much, and thank you all for being here. So when I teach, and one of the courses I teach is this introduction kind of course for non-science majors into astronomy. And one of the very first thing I would always say every time I teach that course is that we're going to do astrophysics, so we're not just going to do pretty pictures. But what I'm going to start with, and we're going to start with, is pretty pictures. But we're going to use them to kind of motivate why we use these very big machines here on Earth and in space to do the science that we do. Just to give you kind of a general overview first, and then I will talk a little bit more about the kind of science that we do. We're just going to start here with our sun, right? And so the way that you might think about the sun is, let's see if this works, is this picture over here. This is just optical or visible light, the kind of light that we can see with our own eyes. But there are many other kind of forms of light. There's a whole spectrum out there. There is infrared light. There's ultraviolet light. There's X-rays and gamma rays, very, very energetic kind of forms of light. And there are radio waves. There's a whole spectrum. And we have all these tools at our disposal, these telescopes on Earth and in space, to study objects. And one of the things you can immediately see here is that even the sun, the thing that we very much need as humans, and that we think we kind of know just looking at it, well, not directly because that's bad for your eyes, but we kind of know what that looks like. Even if you now start looking here at, let's say, with an infrared telescope on Earth, or with some telescopes in space, for instance, that can measure ultraviolet or X-ray light, it looks very, very different. We see different phenomena, and we can learn a lot of physics and how these things actually work, how do stars work from doing these different observations. And this is not only true for individual stars, like our sun, but also if we look at galaxies. Right? This is a different galaxy. This is not ours, because obviously we're in it, so we cannot see it, as we can see other galaxies. But this is a galaxy that kind of looks like ours. And again, in the middle, you see here the kind of light that we can see if you go to a very dark spot and you look up in the sky, or you look through a telescope, that is what you can see. But if we now go to other parts of the spectrum of light, you see other things. If we, for instance, go to the ultraviolet, we see many bigger, hotter stars. If we go to the infrared, there we can kind of see smaller, cooler stars than our sun. If we go to the radio, it looks kind of similar, but actually what we're seeing there is mostly gas in these galaxies. If we now go to the X-rays, it doesn't look like the others at all. So we're looking at very, very different things. And again, we can use these to really understand physically what is going on. And we need all these different telescopes to come to this total picture. And so if we now look into our own galaxy, right, we're inside our galaxy, we can look through it. If we look towards the center of our galaxy, there's a lot going on. And this is, again, a different kind of view. The big picture here is made with the Meerkat radio telescope. Astronomers are well known for using amazing acronyms. Meerkat is actually an acronym for the Karoo Array Telescope in South Africa. And so what you see here are radio waves from a lot of different things. These kind of objects here are the remnants of stars much bigger than our sun that died. We see areas where there are stars being formed. Actually, over here you see, and this little inset here is an image in the infrared with the James Webb Space Telescope, where you see some of that star formation kind of happening. There's funky things happening with magnetic fields that we don't understand yet, a lot of things there. And if we now go to the center, in the center of our galaxy, we know there is a supermassive black hole, a black hole that is millions of times the mass of the sun. And if we use radio telescopes all over the world, all over our globe, we can actually now, since 2018, 19, actually make pictures of these supermassive black holes. On the left, you see the image of the very first supermassive black hole. It was actually not in our galaxy, but a different galaxy for which this was done. And on the right, this is the supermassive black hole in the center of our galaxy, using big radio telescopes all over the world. And so if we now zoom out of this, right, so this is using radio. If we zoom out to the next thing, we actually see these big kind of like pencil beams coming out of the center. This is again in the radio. This is with the Hubble Space Telescope. This is in the X-rays. In this case, you see the same thing happening in all these different forms of light. And what we are seeing here is actually matter, particles being accelerated to almost the speed of light in a kind of a physics regime that we cannot really like do here on Earth. Even the most impressive particle accelerators like CERN in Switzerland or other facilities cannot do this kind of stuff. And the only way in which we can study physics under its most extreme conditions is by using these observations with all these different telescopes and getting these full kind of big picture. And this kind of thing, studying this extreme physics, so studying black holes and other like very compact objects, studying big stars at the end of their lives and exploding, these jets that we see in all these sources, that is kind of at the core of the kind of science that I'm trying to do with all of these telescopes across the spectrum of light. And I'll hand it over to Nick.
Okay. So let me pick up on the galaxy theme again. So this is one of the latest images from the James Webb Space Telescope, which was launched 3 years ago now, I think. And this is a field of the sky that's about 1/10 of the size of the moon. And it's the deepest image we have of our universe. And you can see it's full of galaxies. And some of those galaxies are actually pretty close, our neighbors, but many of them are actually right near the beginning of when galaxies formed. And we think that was around 300, 400 million years after the Big Bang. And you can see a lot of these galaxies are interacting. So so you can see here, there's galaxies that are interacting with each other. There's other galaxies that are kind of just big amorphous blobs. And here, if you look, you can see there's a little red dot. And that was a major discovery of James Webb. And you would say, well, why is a little red dot a major discovery? Well, it turns out this little red dot is at a very, very what we call high redshift. So it's at a period of time when the first galaxies were forming. And we think these red dots are basically, they have a black hole in the middle, and material is falling in to form the galaxy, like the first galaxies that are around. And that little red dot is basically an early quasar or black hole shining in the distant universe. And these are a complete surprise. Nobody expected to find them. They're kind of at a period of time before when the theories said that galaxies should actually be forming. So it's transforming our view of how the universe works. You go from a Big Bang through kind of a period of dark ages to galaxies forming and then evolving, the universe expands, and then eventually you end up with us here on Earth. So to follow that theme a little bit more, so this shows you how we actually use dark matter to look even further back. So this here looks like a very, you see these kind of red things around here. So this is a cluster of galaxies that are merged together, and they're basically dominated by dark matter, which by definition you cannot see. But a prediction of Einstein's theory of relativity is that gravity will bend around any mass. And if you have this big conglomeration of dark matter, it actually acts as a lens. And that lens can then give you extra magnification to go back even further than you can normally observe with the telescope. And these red things here are from that lensing of distant objects. Again, the first galaxies forming. And with this, you can actually look even further back in time. So this is being used to basically map the early universe. And just to show you that on these kind of scales, you basically have clusters of galaxies, these large objects, the largest objects in the universe, that are basically a conglomeration of galaxies here and there, and they actually collide. And all these galaxies kind of move between each other, and the dark matter goes with them. And basically, what you see here, this blue is indicating one cluster of galaxies over here, another cluster here, and they basically have gone through each other. And this red is basically using X-ray measurements to trace the gas that was attached to those clusters of galaxies. And it's actually been left behind, and it's having to catch up with the galaxies that have gone between each other. So it's really amazing. The scales you're talking about here are just amazing. So now coming closer to home, this is, I think, probably a famous picture you've all seen. It's the Pillars of Creation. This is basically where stars are forming. These are clouds of hydrogen, helium, and dust that's basically the birthplace of stars. And this shows you an image from Hubble. This is a very, very famous image. You've probably seen it on posters in coffee shops and whatnot. And you can see basically these dust clouds here. This is an image recently taken by James Webb of the same object, and this is in the infrared. And it turns out when you go to the infrared, all that dust, you can actually penetrate and see through it. And so what here is highly obscured, here you can actually see through it. And this is a different, again, different perspectives. That's why you need something in the infrared and something in the optical. And if you look in radio, and it's kind of emphasizing what Alexander said. And if you peer in, so you look at some of these stars in this cluster, in this cloud, sorry, you basically see new solar systems forming. So you see this is what's called a Herbig-Haro object. And basically we're looking at a new solar system forming, and we're looking edge on to this new solar system. So this is a disk of dust and material that's a protoplanetary disk, which is where planets are going to form out of from this very young star. And it's actually also ejecting out in the perpendicular to the disk jets and streams of material as this whole system comes together. And again, this is this image here, and you can look at it in different wave bands again, in the optical with Hubble, in the infrared, where you see it's, you can actually start to see through the disk. And if you go into the radio, all you actually see is the disk. You don't see anything else because that's what's glowing. So then you ask, well, where did we come from? Where did all the material that we're made of come from? Well, it actually came from exploding stars. So we're going to the other end of the life of a star here, where this is basically Cassiopeia A, which exploded, I think it's like 350 years ago. And all this material is formed in the explosion. Silicon, sulfur, oxygen, carbon, all the stuff we're made of is formed in that explosion. And these different colors denote different elements. And this is actually a mix of X-ray and James Webb data. And so by studying this, you can figure out, well, how much elements were created in supernovae, which kinds of supernovae, and does it match what we see in our solar system in terms of the amount of iron and sulfur and silicon that we see? So that's kind of, you know, you had the Big Bang, and, you know, from there to now and to us, we're kind of trying to follow that flow and how we came to exist. And I'll finish just with this, and this is kind of the next frontier of astrophysics, and I think also kind of our quest to understand where we came from, and, you know, are we alone, which is kind of the big question that's been out there now for quite a while. So this is a nearby star. It's a slightly cooler star than our own, slightly smaller star, and it's a James Webb image. And what we're using here is a coronagraph to block out the light of that star, so we can actually then see what's around it and look for planets around it. And this is one of the first ones found by James Webb, and this is a planet around this star. And this is kind of equivalent to Saturn in our solar system. It's about 20 Earth to Sun radii away. And you can also see this dusty thing here. This is real. This is a dust disk around the star, sort of like our own asteroid belt, if you like. So this is, James Webb is making discoveries here. James Webb is not going to see other Earths like this, because the other Earths would actually be inside where the coronagraph is. So the next generation of observatories, the next big thing, is called the Habitable Worlds Observatory, which is going to be designed with a much more superb coronagraph in the right wavelength range to potentially image Earth-like planets around nearby stars. And not just that, but also measure the composition of the atmosphere around those stars to see if it has the signatures that would support life. So with that, I will go on to the next questions.
Well, thank you very much. So now this question may seem a little bit silly after this presentation, but why do you think the public, the general public, is so fascinated and excited by astrophysics and astronomy news? You've already discussed the photographs in a coffee shop, for instance, but what are your thoughts?
Who wants to start? Okay, so I used to work at NASA, and I think NASA's done a lot to actually engage the public with astronomy and astrophysics, and So when I was sitting on a plane next to somebody, and they asked, "What do you do?" So, so if I said I'm an astrophysicist, they would look at me like, huh? Oh, can you tell me my horoscope? You know, it's kind of like. If I said I work for NASA, they say, oh, wow, that's pretty exciting. So I think it's a combination of, people, you see the sky, you see the stars, you wonder what they are. And, but, a lot of people don't go beyond that. But the stories you can tell about what we're discovering about the universe, about ourselves, and the way that NASA has helped to kind of propel that and make it more accessible to the public, I think that's made it more exciting and then made it easier to justify the big expense for these big observatories and getting the next one and the next one. Kind of each one builds on the next one. So that's my thoughts on that.
So, I mean, I think there's a kind of fundamental thing. I mean, of course, it's kind of hard to say. I mean, for myself, given that I basically wanted to be an astronomer for as long as I can remember. But I mean, looking up in the sky, I think for a lot of people, going to a dark place and then looking up, and there's all these stars there, and you can maybe see the Milky Way and see all these things there, and then these kind of like fundamental kind of questions that Nick also mentioned of like, where did we come from? What else is out there? Are there others like us out there? All of these kind of like really questions, I think, that get to the really being of us. I think that is something that a lot of people find intriguing, and then there was all the pretty pictures that we can show, and even now at a time where in a lot of places it's actually not dark, right? I mean, I think it started hundreds, thousands of years ago where there was no light pollution, but now we're in these kind of places where it is harder to see some of that wonder directly. But then indeed, like NASA and other organizations have caught up on that as well, of just showing what is out there and what we can see. And I think that basically lures people in, and then indeed you can tell with some nice pictures, you can then also tell a really interesting story.
So you've described some of the images and the instruments and equipment that are necessary to sort of explore space from where we sit. And they're increasingly expensive to build. You described one of the next generation, which sounds amazing, but I'm sure it comes at a cost. So what drives the investment in these facilities for fundamental research?
And so again, as I mentioned, having these there's multiple parts of it. One is just the general kind of exploration and getting to learn more, and you need better and better devices to learn more and answer more of the questions. Whenever we observe things, there's more questions raised, and then we try to answer those questions. But also, I think the idea of having exploring all the different kind of pieces of information that we can gather, right? So that whole entire spectrum of light that I was talking about, but also other messengers as well. Now we know that we can, besides just all these different forms of light, there's also other things that we can study, like gravitational waves or exotic particles like neutrinos, and all of these things that really give us more and more information and different views to answer these questions. And so, I think there is that a fundamental kind of like understanding. I think at the same time, and then that I think also gets to the economics of it as well, is that the technologies that you would have to develop for this, right? We're always pushing the boundaries of what is possible, and developing new techniques, new technologies that are not just for us. I mean, they're not just for finding this next new stars or galaxies or planets, but they can then be used in many, many other disciplines, in many, many other fields, and they have a lot of other applications. And that's not necessarily why we do it, but that is something that I think is always there as other things that we can do, and not only to kind of like sell ourselves, like, oh, we can do all these other things as well. But I think it really, it can also be a driver as well. And it's not only these big machines, but also, for instance, big data, right? I mean, so I do a lot of radio astronomy using big radio telescopes, and the databases of radio data are actually among the biggest in the world. As some of the radio telescopes that I've been involved with, and like for instance the low frequency array in Europe, had longest time the record or the largest database, way larger than some of the biggest, kind of bigger than Google, right? Of just the amount of data that is, the volume that is there. And so we're really pushing there the envelope of what is possible. So I think there's also this drive of people like, oh, wouldn't that be really cool? Let's find a way to actually do that. But that comes also with a certain expense, but then we try to have also a good story that justifies that.
Well, on the expense side, I looked up before this talk, if you inflation adjust, the James Webb Telescope is cheaper than the Hubble Telescope. So each of them, James Webb, I think about $10 billion. Hubble Telescope, about $11 billion in 2015. So, that is a decrease in price. There's deflation for space telescopes. I don't know, maybe technology is driving down costs. That's the best possible explanation here. So, it's possible that the next one can be a mere $9 billion. And if you want to scale, I tried to think of things like, okay, how can you conceive of $9 billion or $10 billion? $10 billion is about 100 F-35 fighter jets. It's also about the cost of the Purple Line in Maryland. So, you can make your choices what you want to do with federal dollars.
Yeah, so I kind of agree with what you said. Actually, the Hubble was a little bit more expensive because they actually made it serviceable. And so that was the initial cost. But then they actually went out and repaired it and then added new instruments, which every instrument sort of took advantage of the new technology that was available as time marches on. And so it's the same size mirror, but you put in a much more sensitive instrument behind the telescope, and the astronauts would go up and pull it in, push it out, whatever. So it actually ended up being like 20 billion.
Cheaper.
And so it was a lot cheaper, exactly. But that is something, serviceability of observatories in space is actually a big thing, and it's now mandated by Congress that if NASA builds any future major observatories, they have to be serviceable because of this upgrading thing where you can really, a mirror is a mirror. Once you got a mirror, it's kind of, hard to add to it. But the focal plane technology changes dramatically over time, and so you want to take advantage of that.
And it might also be good to emphasize, because there is definitely a big difference in putting something in space versus building something on the ground. But I think the good and the bad thing is that we have an atmosphere. The good thing is for us that we're actually protected against X-rays and gamma rays and ultraviolet light and all those kind of things from space. The bad thing is if we then want to observe these things in space, we actually have to put satellites in orbit or further away from Earth because it doesn't get here. So that's why if you hear about some of the really big optical light kind of telescopes and radio telescopes, that light actually comes through the atmosphere. So for that, we can build big telescopes here. And especially in radio, there is a technique called interferometry where you use multiple different dishes together. And so you can kind of like build that out over time. So you can even start with some and then you say, oh, we're going to add a few more and a few more. And so build it out over time. So you can kind of spread out the cost a little bit, which is also being used sometimes to manage things. But unfortunately, good for humanity, but unfortunately for the astronomers is that you have to put some things in space and it is just more expensive.
So what kind of roles do CCAS faculty play in supporting these endeavors?
You should start with that.
Sure. So in the physics department, our astrophysics group, we in general, we are what we call a high energy astrophysics group. That is not only because we are just running around in the hallways. So we study objects that have a lot of energy, as I mentioned before, have very basically very extremely energetic objects like massive stars exploding, black holes, or other objects that have big eruptions, have things where you can really study extreme gravity, extreme magnetic fields, all of these kind of things. And so we study those in different ways. One is from a kind of an observational point of view, using all these different telescopes, the different satellites, ask for observations, get these observations, analyze these data. Of course, we do this. I have lots of graduate students who are involved in this as well, undergraduate students as well. And so that's the kind of observational side, but then also we have actually a partnership with NASA Goddard Space Flight Center where students have an opportunity to be involved in building some of these new instruments, especially those that go into space. And actually work on the hardware, detectors, software, all of these kind of things. And that's ways in which we're contributing to this as well. And then also on the other side, there's the computational side. I already mentioned the kind of big data, but also including high-performance computers here on our campus, like Pegasus, for instance.
Cheers to the high-performance computing cluster.
Exactly. And so... And so that's also something that we use, and in all of that, really trying to push forward our understanding of these objects.
Yeah, so something I'm doing is, so NASA has these programs where that you can actually propose to do a mission or do an observatory. So there's kind of two classes of missions in NASA. There's the big ones like James Webb and Hubble. Those are what are called strategic missions, and they're just done by NASA. NASA selects them through a National Academies process that prioritizes them, and they're just managed by NASA. But they have a smaller class of missions called Explorers, Discovery, Probes, and many different names, where basically any person, qualified person, comes up with an idea, and you write to NASA a proposal for $300 million to build a space observatory. And so, when I was at NASA, I was involved with this quite a lot, especially trying to encourage PIs at NASA and at universities to propose. It's actually not as easy as just, you write a little proposal. They're usually about this thick and, involve a lot of people. You have to get industry involved and NASA centers usually. So I'm kind of pursuing a mission to do some of this extreme environment stuff that Alexander mentioned. So I'm what's called an X-ray astronomer. So I study X-rays from extreme environments. So material falling into black holes, how black holes are created, where they come from, and when black holes merge and collide, and this kind of thing. And part of what you see from that is both X-rays and gamma rays. And so what I'm trying to do is propose a mission that will use these very luminous explosions when black holes are created to track this all the way back to the very early times of the universe, the kind of periods that James Webb is looking at, and to use that both as a probe of what's going on with these exploding stars, and also just to use them for the extreme physics that's going on in these things, because it's physics you cannot create on the Earth, fortunately, because if you did, it would not be very pleasant. And it's basically using the universe as a laboratory. So I put this proposal in with the support from the dean and the university, and also with NASA JPL. In about 4 years ago, we put it in, and we didn't succeed. But it was a large effort. We had like 80 scientists involved from around the world, and we got a lot of good feedback from the review. And so we're going to try again whenever NASA does the next opportunity, which will probably be in 1 or 2 years' time. So that's one of the exciting things you can do as a scientist is to actually propose to get a slug of money from the government to build an observatory. And this is something I'm very passionate about, and I'm sure you would be if you wanted to take advantage of that kind of opportunity. So that's something else that we are doing here at the university.
Thank you. So what role does this kind of fundamental research play in workforce development? Dr. Vanderhorst mentioned earlier the role that students can play in the research going on here on campus. But what role does fundamental research play in workforce development?
I mean, I can't tell you anything specifically about physics, but I can tell you that money attracts people. That's what I can tell you as an economist. So if money attracts people and you want to get good people and you offer them money, you can get more people. And furthermore, scientists like to work with other scientists. Even though you might think that scientists could be a bit introverted, which I think is true, they still like to work with other scientists. And in fact, economists show that people are more productive when they work with other people, and particularly when they work with other people who share similar expertise. So by giving money, it's not enough to just get one scientist. Nick, while a great guy, all by himself, may not be too productive. He needs the other 79 people on his grant application to make a fantastic grant application. That's why he needs $300 million, not, just a couple $100,000 to cover him. So first, money brings people, and one person alone is not enough. You need money to bring a group of people, and then you can think of those people as delivering scientific outcomes, which my colleagues have told you about. You can also think of those people as getting trained in using a particular set of skills, and then they go off to the labor force and take those skills into other jobs. So they may not use their scientific training in physics. They might go work for a hedge fund on Wall Street and make a ton of money. But using, I think, a lot of the skills that Alex has taught them.
Mm-hmm. Yep. Yeah, no, absolutely. So I think, just an example for that last point, when we look at the, let's say, alums just from our program, right? I mean, we actually have, if we just look at the astrophysics group, and when we look at the PhD students, those that get PhDs and then go on from there, many actually get a postdoctoral research position at universities or, let's say, at NASA centers or other research institutions. But then from there, they would either keep going on this kind of like academic or research path, or go into other directions where they use those skills in many, many different areas. Their data science skills, their analytics skills, there's a very big range. And the same is true for our undergraduate students. A lot of them will go into grad school, but many others go into other careers, and they're extremely successful. I mean, we had about a month ago, we had during the Alumni Families Weekend, we had an alum panel with people graduated from like 5 years ago to 20 years ago. And the range of careers and the amazing success that they've had is absolutely fantastic. And where they apply those skills, and it's really all over the place. And we always say, like, I mean, not only for astrophysicists, but physicists can do anything, which may be a little out there. But the thing is, there is a very wide range of skills in terms, not just the technical skills and knowing how to solve an equation, but it's the problem solving, it's the analytic skills of knowing how to take a big problem and chop it into smaller problems, because that's what we have to do all the time when we do research, and then solve those and then put the puzzle back together. There's all of those that are extremely valuable everywhere. And so that is really what we do, and that's that training component, and it really helps the entire workforce, and especially nowadays. I mean, having a really strong overall STEM workforce is extremely important for our society, and and I think that we're doing our part in that.
Yeah, so going more to the funding side of this, so within NASA and also at NSF, I can speak to the NASA more authoritatively, it's not just building these massive observatories, but the NASA has funding that goes along with it. So if you propose to use the James Webb Space Telescope, you get money. If you succeed in writing a winning proposal, you'll get money, maybe $70K or $50K or $100K to fund your analysis of that data and to make sure it gets published. And you usually use that money to hire a student or a postdoc. And that is part of the kind of the STEM part of what NASA's trying to encourage is a pipeline. So it's not just you get the money and you pay yourself or whatever, or your travel, but it's to bring on new students who then become postdocs, who then become faculty or whatever, or maybe go off to industry and take other careers. NSF has similar grants, but they're not tied to any particular telescope. They're just more science-driven, PI-driven. Another aspect of this is in the NASA research and analysis programs, there's a lot of money goes in for technology development, instrument development, which goes into a large part of it goes into the universities to set up labs to develop new detectors or new telescopes or whatever. And again, that fosters students, postdocs, to kind of develop and learn hands-on skills. And there's what's called the suborbital program at NASA, where you build a little experiment, stick it on a rocket, and it shoots up and comes straight down again. And that's used to kind of both develop technology and get some quick science. And the turnaround time is such that you can do it within the career of a PhD student, or even a summer student in some cases. There's also balloon payloads where you have a big balloon and you hang a payload beneath it and use, put telescopes on balloons and get above the atmosphere, at least some way up above. So these are programs that the agencies have to encourage both technology development, analysis of the data, but in particular the pipelines, so that it just doesn't end when that PI retires. There's another generation to take it on, which may have even better ideas.
Thank you. So we've mentioned NASA, we've mentioned NSF funding. What about the role of private industry? We've certainly have seen more private industry involved in space exploration. So what's the role of private industry, and how do you expect that to change over time?
You want me to start?
Yeah, let me start. Yeah.
Yeah, so it is evolving at the moment, that's for sure. Usually for things like James Webb or even the Explorer, the mission I was proposing and will propose again, industry usually does the spacecraft. So, you can, believe it or not, they have a catalog of spacecraft and, I want one that will do this, that, and the other. And they usually have a catalog and you say, I'll take that one. Then they build it. And so that's a key role. It used to be NASA centers would do their own spacecraft, but that's kind of going out of style because industry can do it. So that's one aspect of it. Another thing that's, well, I guess it's always been there. You need to get the things into space, so you need a rocket. And so industry provides the rocket, and that's where a lot of change is happening at the moment. It used to be, you use a rocket once and that was that. And they were very expensive, and then you wanted to make sure everything worked. That paradigm has changed initially with SpaceX with reusability, and now other rocket companies are doing the same thing. So obviously industry is absolutely critical to get your stuff into space. I think even within industry, you get research groups because they want to be savvy about what they're doing. And so some companies, like Lockheed, for example, have a cadre of scientists that study the sun. And so industry does play a role in some of the research that goes on because it's in their interest to have knowledgeable people on their side so that their products are actually responsive to what the community needs.
And so another kind of example of this, and maybe I should have clarified earlier that because we have to talk about NASA and National Science Foundation and NSF. So in astronomy, there is this funny thing where everything in space is NASA and everything on the ground is NSF. And there's a very kind of clear divide, which actually, especially because we want to look at things in such a kind of all across the spectrum at the same time, this is changing, but that change is pretty slow, I would say. And slower than some of us may want, but that's a different story. And so on the ground, right, what we've seen there, I do a lot, as I mentioned before, with radio telescopes. And there's currently a radio telescope that's going to be built. It's called DSA 2000. It's a Caltech-led facility. The 2000 means it's going to be a radio telescope with 2000 dishes, which are going to be very close together, and it's going to kind of work as a radio camera of the sky. and it's going to be a phenomenal thing. And so a very large part, and depending on if they're going to get more funding from the NSF or not, maybe everything, well, not everything, but because there's money coming from the university, but a very large part of it is actually coming from a foundation. And so there's now this kind of foundation money going into, so that's not necessarily industry, but they are definitely connected to industry and partnering with industry partners who can potentially come up with innovations, new technologies that also make things much cheaper, and so that is then better manageable by the foundations as well. So there's a lot happening in that space. There's many more new players than just as before, where you had NASA and you had NSF, and then at the universities and the centers doing their work. There's many more actors in the game now.
So I'm going to agree with all that. And then I will also say, from the economist perspective, we will never expect private industry to do anything that does not make money. All right. So if you want something that you anticipate could make money in 50 years, that is not a project for private industry. That's why we have the government funding NASA. The government can fund things that have a delayed payoff, a very uncertain payoff, a payoff that doesn't return, that returns in potential science value, but not in market value. If you want something that returns in market value on a reasonable time frame with a reasonable expectation of return, then look for private industry. And I think what in the best of all possible worlds, what the government funding does is it provides, you can think of the government funding as entering a lottery, sort of a lottery for innovation. And the government has enough deep pockets and enough time to enter this innovation lottery that a private company will not, because the private company has to make money on a time that shareholders expected. So the government can enter the innovation lottery, and the government is not going to always win. So my father is a physicist, trained as an astrophysicist, spent his entire career working on nuclear fusion. Nuclear fusion, we still don't have it. So that is not, I don't think that is yet a winning lottery ticket. Maybe, maybe 25 years from the future, it's gonna be a winning lottery ticket, but not yet. Government put a lot of money in. I don't even know if there are private sector outcomes from nuclear fusion investments that the government has made over the past 40 years that you can claim are the result of those funds. On the other hand, I think you can claim that there are private sector market valued products that come from NASA investments, SpaceX, Blue Origin, commercial satellites, all kinds of things that are now private market deliverables that you can make on a time frame that are going to pay off for private investors, come as a result of a certain number of winning tickets, from that public investment lottery. And there's a lot of losers too. All right, don't think that all the tickets you buy are winners. There's a bunch of losers, and you can't know in advance which ones are the winners. That's why you need the government to take that risk, a risk that the private industry is never, ever going to take.
Thank you. All right, well, let's turn to you all for questions. All right, I see a very enthusiastic hand. Alex?
This is perfect. Because so based on kind of what was said here, and some of the things that you just mentioned, I'd be curious to know, is there a thought that maybe is one more harmful than the other, or is it all still just helpful? It doesn't necessarily matter where the funding is coming from, whether that be private funding or government funding. Does that make sense?
I guess from an economics perspective,
You need to
we
repeat the
wouldn't.
question.
Oh, sorry. I'm supposed to repeat the question. Does it matter where the funding comes from? Is it helpful or harmful whether the funding is private or public? I'll let them speak for their actual experience. But from my experience, what I would say as an economist is that there are things that the private market will never fund. So, if you want the James Webb Space Telescope, you're not going to get that with private funding. But there may be ways in which private funding can helpfully work within sort of university research, but probably not at that scale.
So there is a kind of, in science from space, there is a shift going on at the moment, especially for earth science, where we're basically looking down. It has been the tradition that NASA and other agencies have built missions dedicated to just studying the planet Earth, and there's obvious things like weather forecasting, But there's other things like monitoring how the ice is melting on the polar caps or how the ocean depth, like stuff like that. So there's moves afoot to try to commercialize that. So the industry basically puts up a satellite that takes pictures or measures methane or whatever it is, and the government buys back that product. So the government isn't saying, I want a satellite with XYZ kind of instruments on board and this cost. But government says basically, I need to measure methane across planet Earth to this scale, and I'm going to put a bid out, and we'll pay so much per image or per measurement or whatever. And the company takes some of the risk, and they also make profit off it as well. It's a little controversial. Some, feel that this is a rocky road to go down because you're basically straitjacketing yourself into what industry wants to provide you as opposed to what maybe you really need. So there's a bit of a culture shift going on, but that is something. And there's a new NASA administrator that's hopefully going to be confirmed soon, who is, I think, advocating for that kind of thing, and certainly industry is advocating for it quite strongly. So I think there is a change going on between what industry is willing to invest in versus what the government needs to just fund straight up and own the satellite that's in orbit.
One other thing, and not directly industry, but I think again the kind of like alternative partners in the whole enterprise is again some examples on the radio astronomy side is that there have been some big radio telescopes that have actually been kind of saved because of other partners stepping in. For instance, there's a lot of funding going into the search for extraterrestrial life. And there's some people who have a lot of money who really want to fund this. And they will buy time on big radio telescopes to do this. And that money is being used to run those radio telescopes. So they will have a certain amount of the time on the telescope, and then we astronomers can happily use a very nicely maintained facility that we use for our science. And other things there is actually on the also on the military side as well, right? Where some of the radio facilities are a lot of time, for instance, go to the Naval Observatory or other kind of partners like that. And so there's these different kind of groups that come in. And for some of the facilities, especially also some of the older facilities, they're working perfectly fine. And there are some astronomers that would very happily keep working that for decades. But then at some point it's like, well, should we actually build the next big new thing? And then they will look for other partners to then say, well, we can keep this running. You will just lose some of your time on this facility, but you can still use it, and there's still enough to kind of go around, and then everybody wins. So it's a different kind of approach.
Yep. Yes.
It's a science question. So, how is the James Webb Telescope? Has it helped anything with particle physics? Okay, and also about quantum gravity and things like that. Those concepts, whether it has helped to understand more of those type of things.
So the question is about if James Webb also helps with quantum gravity, particle physics, all those kind of things. James Webb is primarily, as some of the examples that Nick showed really are in the distant universe or those areas where there's, for instance, a lot of dust, where you can look through those kind of environments. And that is really where most of its, let's say, power really is. But again, as part of a larger kind of thing, right, of a larger suite of telescopes, it plays an important role, right? Where you, in some cases, if you do want to understand better what is happening in some of the, let's say, X-ray or gamma ray observations, where you're really probing those fastest moving particles in space, sometimes it really helps to have also the picture in, let's say, optical light or infrared light, and to fully comprehend what is really going on. And it's not sufficient to only have this one, like a gamma ray telescope that just finds these particles, because you need a bigger kind of context to really understand what is happening. Not that sure about the quantum gravity thing, but definitely for the kind of particle astrophysics, again, they are having this larger across the whole spectrum view is crucial in a lot of cases.
Long?
Can you talk more about the Nancy Grace Roman telescope, what it is, and where it's getting funding from?
So the question is about the Nancy Grace Roman telescope, what it is and where it's getting funding from. So that is the next, what NASA calls Great Observatory. So it's the next one after James Webb. Hopefully will launch next year, sometime in the fall, perhaps. It's wholly funded by NASA. So James Webb is basically a large telescope that's designed to work in the infrared to go very deep in the universe. The Roman telescope is basically it's the same size mirror as the Hubble Space Telescope, but it's designed to be a very, very wide field of view. So that field I showed you from James Webb, that was about the same size as the one from Hubble. It's a few arc minutes across. For Roman, it's got a massive focal plane, and I actually forget how much bigger it is than the one from the Hubble Deep Field, but it's very, very large. And it will capture, it's basically like a survey instrument, so it will capture large chunks of the sky, and it will go about as deep as Hubble, but because it's doing such a large chunk of the sky, it enables a large swath of new science. It was actually one of the key science drivers for that mission is to measure this thing called dark energy. And this is actually getting back to some of the fundamental physics stuff. So, 70% of the universe is this mysterious dark energy that nobody knows what it is, but it's causing the universe to expansion to accelerate. It's one of the kind of biggest Nobel Prize winning discoveries about 20 years ago. And so this Roman is designed to basically use two different methods to measure what's called the equation of state of dark energy. One is just measuring bright supernovae going out to high redshifts, and another is, if I get this right, I think it's doing, is it lensing or is it, it's lensing, yeah. There's a European mission that does the other one. And so it'll do two different independent measurements, and it's almost like a fundamental physics experiment. But it'll also do a lot of other things in terms of surveys of large chunks of the sky, which can be used for a lot of other things.
And one last question. Evie?
So you guys have talked about the partnership between private industry and NASA and other institutions in making great physics or astrophysics happen. But what about the large constellations of commercial satellites for, say, providing internet power in a plane? What's the impact there?
So the question was about the large constellations that are out there in space now. So we had a really nice conversation with lots of nice questions, and you're trying to make us mad at the very last question. Okay. So those large constellations providing broadband internet and band internet in different places and stuff are wonderful for some, but not as wonderful for others, for astronomers, for instance. These, if you have tons of these little satellites zipping through space, they reflect light, and that light that they reflect, we can see with our telescopes. And so one of the things that I really like to do, and many in the astrophysics group here, is looking for these little blips in the sky, because they indicate very fast changing things. So looking for these stellar explosions that are billions of light years away from us and have really, really interesting physics behind them. And those constellations make that very hard. And it's not only the reflections of that light, of just visible light or visible telescopes, but also all these little satellites have little radio antennae. And those little radio antennae send out little bursts of radio waves. So if you're then looking for little bursts of radio waves in space, then that is really making it very hard to find them. And luckily there are ways to do this, but it is becoming harder and harder. There's various groups that are working on trying to protect, make sure that certain radio bands, for instance, are protected, that some of this, that the satellites have very, very black paint on them, so they don't reflect anything. And so, but even some of the blackest paint that we have is not enough to actually not see them. And so, yeah, there's huge challenges there for astronomers, especially those that are looking for varying things. If you're looking at objects that are basically just the same over millions of years, you just observe longer and it is all fine and you filter out that data. But if you're looking for very fast changing things where you can do this really exciting extreme physics, it does make it much, much harder. And we have to think very carefully of how to filter out those things. And we're getting better at that, but there's also more and more of these things out there.
I will say, we in economics have a partial solution to your problem, which is when we see people doing things we don't like, if we can value how much we don't like it, we can charge people a tax equivalent to the value of our dislike. And then you can use the revenue from the tax to fund your solution.
Okay.
Okay, so we ended tonight with challenges and possible solutions. All right. Well, thank you all for being here. I want to thank the panelists for sharing your expertise with us today. I want to thank the SMPA team for being here to film. This will be put up online later on, so thanks to Jack and the team for putting this together. I want to thank the Columbian College staff who helped put this, organize this, and to manage this. So Beth Warren, Max Koger, and of course, Associate Dean Evie Downey. So thank you all for being here today, and join us outside for a reception to continue the conversation. Thank you.